Let us come to lecture 22. So, we have seen situations where solid solution and liquid solution, they have a different enthalpy of mixing, and that is what you are getting eutectic phase, or in some cases congruent phases. And if enthalpy of mixing of liquid solution is highly negative, you could see that the liquid stability increases, that means the liquid is stable at a much lower temperature. And in case of a situation where enthalpy of mixing of solid solution is highly negative, then I could see that the solid phase is stable at a very high temperature, and we get to see congruent melting phase. But whatever discussions we had, we could see that the solid solution, they are forming from 0 to 100% B, they have same crystal structure. That was basically the basic assumption. But situation could be different, that even if the enthalpy of mixing of solid solution is positive, then also I could have a different crystal structure of the solid solutions. And that time situation would also lead to eutectic phase diagram, but we cannot continuously draw the phase free energy line for solid solution. So, that time two different phases would have a different free energy line, that means the G2 lines. Now, in one case ΔHmix of solid I considered 0 greater than 0 and ΔHmix of liquid equal to 0, that time we could get eutectic phase diagram. Now, another situation where del x, and that time in this situation I could see that this is G, this is x b, the G2 of solid solution was like this, because that time we consider A and B both have same crystal structure. And one example for this particular phase is copper silver, where I could get an eutectic phase diagram, but their solid solution line would be like this, continuous from 0% copper to 100% copper, and let us say this is copper, this is silver. So, I could get a continuous line. The situation is different even if ΔHmix of solid is 0 or less than 0, and of course, that time ΔHmix liquid I can either consider equal to 0 or less than 0. So, in these situations, and if we see that the composition range and different composition levels, I could get different phases of different crystal structures, then we have to consider the G2 line of those phases separately. And those phases would have limited solubility, that means it can take some second element in the solution to certain extent, but it cannot take it up over the entire composition range, and that would lead to a change in the shape of the G2 line of those phases. For example, in case of aluminum silicon, their aluminum is FCC, but silicon is diamond cubic, crystal structure, and if I try to see silicon and if I try to incorporate aluminum into it, silicon would never contain any aluminum in it. So that I could not get any free energy line, that means G2 of silicon, and where aluminum is mixed, that means aluminum becomes solute, it is not possible. That means these two cannot form any alloy. So, that case there is no need to consider the solution thermodynamics or solution formation in case of silicon, because it cannot contain any aluminum. So, that time the free energy line would be simply a single line, it cannot have any curvy nature like this. This would be my G2 of silicon, because it has only one composition, which is 100% silicon. Now, on the other side, aluminum can incorporate silicon little bit, and that percentage is very limited, maximum around close to 2% it can contain in the solid condition. So, in the solid state, here also I am talking about the solid silicon. In the solid state, aluminum can contain 1.65% silicon maximum. This is the maximum limit of the solubility of silicon in aluminum. So, here I could see that maximum 1.65% silicon, it can go into aluminum in the solid state. So, solid solution is a limited solid solution. So, that case I cannot extend this aluminum G2 line, that means G2 of solid aluminum alloy, where silicon would be the solute, would be again G1 plus ΔHmix. The extent of G2 line would be very short. So, I mean to say G2 extent of G2 line means, if I try to plot this is X B, or in this case it will be X silicon, and this is G. So, this would be my G2 aluminum silicon. So, this will be shorter, not extending to the entire range of compositions from 0% aluminum to 100% silicon, because it cannot contain that much amount. And if it is intermetally compound, this gap would again further shrink, and it would become, let us say, if we try to see a free energy G2 line for XB, some intermetallic forms, that time that free energy line would be very much like this. So, it cannot have very wide alloy formation or the composition acceptance. So, if I try to plot phase diagram for aluminum silicon system, so the phase diagram looks like so silicon melting point 1414 degree Celsius, this is silicon, this is aluminum, and this melting point is 660.7 degree Celsius. So, I could get maximum of 1.65 of silicon percent, this is in terms of weight percent of silicon. This becomes my eutectic temperature, which is 577 degree Celsius, and the eutectic composition is 12.6% silicon. These are all in terms of silicon. So, I get phase diagram like this. So, where this is liquid plus silicon and this is, since it contains little bit of silicon. So, I could say that this is alpha, the solid solution of silicon, solid solution of aluminum, and which contains silicon as a second phase, silicon as a solute. So, this is alpha plus liquid phase and this is alpha plus silicon. Now, if I try to draw the free energy composition diagram at this eutectic temperature, the free energy composition diagram would look like this. So, that time silicon would have a plain line because it cannot contain any aluminum, one straight line, and this is my liquid line and this is my aluminum line. So, in this case this is composition of alpha, this is the composition X eutectic and this is the composition X silicon. So, I have a phase diagram like this. Now, if I try to choose a composition like this, that time again as per our understanding we have to draw a tangent over this, and then the formation of silicon, if it has to form, then my free energy barrier would be this to this. So, this becomes my delta G n as per our previous understanding. Now, what I mean to say that if the crystal structures are different for the phases which will be in equilibrium, they will not touch, that free energy line will not be continuous, because this line is not going to match with the silicon line. Now, situation could be, one arbitrary situation could be like this. This is my liquid line and this would be my solid 1 alpha phase, and let us say this is my solid 2 beta phase, and I could have a common tangent. Then this would be X alpha in equilibrium with liquid, this is X liquid in equilibrium with alpha as well as beta, and this is X beta in equilibrium with liquid. Now, interestingly, in one of the situations in case of copper silver, I could see that they were continuous line, this solid, this is solid G2 of alpha, this is G2 of beta, and this is G2 of liquid. So, they were continuous, but since this alpha and beta they have different crystal structures, that is what we are not able to connect this entire solid solution line. This is the difference when I have different crystal structures, and here also I am getting eutectic because this liquid is in equilibrium with two different phases, and that time these composition would disintegrate between two solutes, two alloys. One would be having composition X alpha in equilibrium with liquid, and this would be X beta in equilibrium with liquid. And when we had similar crystal structures, we used to indicate as alpha 1, alpha 2, but since here they have a different crystal structures, so that is what we are giving two different notations, alpha and beta. That means they have different crystal structures. Now, on that basis, we can explain aluminium copper system. This aluminium copper system is highly important from technological, rather engineering sense, because this system gives us an important alloy which is called duralumin. Generally, this is an alloy of aluminium, 4 to 5% copper, and this basically in weight percent. And duralumin also, it's basically we call it 2000 series aluminium alloys. This duralumin has got a tendency to get age hardened, and that is what we get to know the concept of age hardening. That means with time a material can get harder and harder, so the mechanical property becomes much better and better from the point of view of strength. The strength increases to a great extent, because aluminium, if we see pure aluminium, it could have a strength of about 100 to 120 MPa. But once we have aluminium copper system, and that too around 4 to 5% copper, and if an aluminium and copper they are in solution, the strength improves, definitely strength improves because of the solution, solid solution hardening, but that strength improvement would be very minor, maybe around close to 1. If it is 100, then it can, if the pure aluminium has a strength of about 100, it can improve by almost about 120, something like that. But interestingly, if that solutionized, that means everything is in solid solution, that alloy is taken to a low temperature, and if it is kept for a long time, then gradually the strength increases to a great extent. It can even go up to around 300 to 350 MPa. So that means almost about 3 times increment in the strength, which is remarkable, and this remarkable strength increment comes from the concept called age hardening. And this age hardening, since we are the way we have started, that aluminium copper 4%, let us say, it is to be in solution, and then it is to be taken to room temperature, and then it is to be held at that temperature for a long time. So that means we are talking about temperature and time. So because of that, we get increase in strength. So this strength increase, that means it's fundamentally it's related to age hardening, and that is dictated or the controlled by temperature and time. That means the time, temperature where you are holding it, and time how long you are holding it. So actually this relates to processing, which is decided by the heat treatment condition, because nothing but the heat treatment. Now we are talking about room temperature. Since the room temperature diffusion is sluggish, so if we put it at a little higher temperature, let us say around 170 degrees Celsius, this hardening process becomes quicker. Though the overall hardness would be lower, but it would become, the process becomes quicker, which is of great advantage, because the industry does not allow much long time, because the long time of operation means the cost would increase. But depending on the requirement, again I am coming to that part, the requirement part, if we require this much of strength, and then we have to see how quickly we could attain that particular strength. So depending on that, we choose the temperature as well as time. That means if we go a very long time, then it might happen that instead of increment in strength, there could be decrease in strength. So that is what we have 3 stages of age hardening. We call it under age, peak age and over age. So that means this aluminum copper system is an important system to look into, so that we could understand the concept of age hardening. Now, but we have been looking at the phase diagrams. For the entire last 10, 12 classes, we talked about phase diagram. Now, what could be the importance of that phase diagram? So, there should be some importance of the phase diagram with regard to heat treatment. Now, if I try to see some phase diagram, let us say I try to see a phase diagram, eutectic phase diagram. So, this is my eutectic phase diagram. This is liquid, this is alpha plus liquid, this is alpha, liquid plus beta, and this is beta, this is alpha plus beta. Temperature xb, this is A, this is B, and this xb is basically the mole fraction. This particular temperature is nothing but the eutectic temperature, this is eutectic compositions. Now, entire diagram has been drawn on the basis of equilibrium between different phases. And when we talk about equilibrium, we are drawing free energy composition diagrams. Now, once we get this diagram, that means if I, let us say, I take these compositions, when it is very high temperature, if the temperature is this one, then everything will be liquid. But as it comes down, if the temperature drops, at certain point of time it will appear, it will come and touch this particular solid liquid phase line, and the solid liquid phase line is nothing but the equilibrium between solid solution and liquid solution, and that time I could get first alpha phase, a sprinkle of little small nucleus of alpha phase. Now, as we go down the temperature, I could see that the alpha phase is forming with a different compositions, but if we give a very long time, then these composition and these composition and the liquid composition is also enriching. That means, if I am here, let us say at this temperature, the composition of the liquid solution would be this one, and composition of alpha solid solution would be this one. So, that means that liquid phase is disintegrating into two different compositions. So, that is what you need diffusion. Now, as we go down, then I would come to this particular region, this particular eutectic temperature. Once we reach to that eutectic temperature, then the remaining liquid, so we are getting solid phases as we are going down. So, the liquid content is decreasing, the volume of liquid content is decreasing. So, the last liquid which is to be solidified, that will have the composition of eutectic, and that eutectic composition, once we achieve this composition, it would disintegrate between beta and alpha. So, the alpha phase and beta phase would appear at this composition, but initially it will contain. So, that means liquid, it will start getting alpha volume fraction increases, liquid volume fraction decreases, and then the last liquid will achieve eutectic composition, and then once it achieves eutectic composition, it would have eutectic reaction, which is nothing but alpha and beta with a composition this x alpha beta, and this is x alpha, this is x beta. So, x alpha and x beta. So, these two compositions it will form. So, now from this phase diagram, I would be able to tell what will be the possible phases that could form during cooling or during heat treatment or during holding. All those things can be obtained from this phase diagram. That is the importance of the phase diagram, because we must have the knowledge of phase diagram that would tell us that what phase would appear. Otherwise, we will not be able to do any justice to the heat treatment process. Thank you very much.